That time is up. So Control C, Control V, right? Times the derivative of the exponent, which is 31 x squared plus 1 to the 30 times 2x times ln 4, walk away. So now all of this is f prime of x, which is the exponent. It contained chain rule itself. Why do we want to know exponents of these functions? Because we can, exponential functions. Exponential functions are present in almost every endeavor of our of human existence. Let's put it that way. You have.
It's a shortcut, right? We could just always use some sort of ungodly chain rule for it too, right?
No, this is the only way to do it, unless you want to do the limit.
You can't chain rule it?
That is chain rule. This formula is a chain rule.
Okay.
The derivative of exponential function is itself times the chain of the exponent times the chain from the base, because it's not e.
Oh.
Now, that's one thing that I didn't point out, which I feel ashamed for now. So if this was e to the x, then b would be e, and each of these would be x, and this would be x would be 1, right? So look at this. The derivative of e to the x is e to the x, because you get e to the x on the right, and then this term is 1, and ln of e is 1. So e to the x times 1 times 1. This is the formula that it's the master formula for all possible cases. It looked funny from this end. So, as I said, exponential functions model almost every aspect of our existence. Think about it. The world of finances dominated. The compounding interest, the continuous compounding, all of those formulas are exponential formulas. There are no loans of any kind without it. So, world of finance. What else do we have? World of engineering. You want to talk about electronics, you will have to talk about capacitors and inductors. Both are charged and discharged through exponential functions. Those are essential components of any electronic circuit. You want to talk about, let's say, environmental issues and problems. We have the decay of garbage, decay of radioactive decay of elements after any kind of nuclear catastrophe, whether it's fission plant exploding or, throwing the nuclear bomb. Radioactive decay is present. Talk about carbon dating for history, right? For archaeology. Carbon dating, again, decay problem. Medical field and how the drug metabolizes in the body is going to be, again, exponential function. So these exponential functions technically govern almost every aspect of what we study, and that's why they're so important. And we are just so damn lucky that these functions are so abundant and so easy to integrate and so easy to differentiate. So as just like lucked out. Now, biology, talking about population, for instance, we can say that, population started with 500 and then e to the, I don't know, some kind of k, so I don't know, 1.3 t. And this is a population model. You look at this population model and you say, well, I can actually differentiate this and get the instantaneous change of population at any time, at any given time. So You can find dp dt, which in this case would be 500 e to the 1.3t times 1.3, which is what? 650 e to the 1.3t. So we have the population model up there. This over here is instantaneous change in population. So I want to know how many these, whatever it is, cats or rabbits or bacteria, how many are there in 10 years? We are going to, right, use that to figure out the population. But how much it's changed at the 10-year mark, we use this formula here. So this one calculates the change at the time instant. So that's what the derivatives do. So you find whatever formula is as exponential given, or you figure it out, and then you take its derivative, and that will measure the change. In terms of distribution of a drug in the body, you can come up with a model because, guys, every drug has half-life, just like radioactive materials, just right, because it's going to dissolve, it's going to metabolize in the body. So if you go, let me see what we can do in terms of, I'm going to use Wolfram Alpha because my Mathematica doesn't work right now. Let's take a look at Advil.
You do caffeine too. It's about 6 hours for caffeine.
Yeah, I wouldn't know because for me, coffee will keep me up for days. So as you type Advil or any other medication in Wolfram Alpha, right, you will get all of the aspects of that drug. You get the chemical composition and as you can see, the Lewis structures and everything else. You can cook this if you know how it interacts with other medication and so on. And there it is, biological half-life 1.9 hours, call it 2. We can use that piece of information to come up with mathematical decay model, which is actually how fast it metabolizes in the body. And you can figure out. Now, there is going to be a decay model. And what do we know about decay models? When does a decay model hit 0? They don't. So this is your initial dose D, 500 milligrams. And this over here is the infinite time, which you're not else. So sorry. Everything you ever took is still there.
I could tap into all those reserves with that game. That'd be great.
So I can find how much metabolizes after an hour, after 2 hours, after 3 hours, because those are those slopes of tangent lines you asked about. That's what they measure, milligrams per hour. So you would know after the first hour, right, at hour 1, this many milligrams dissolved, metabolized, and so on. If you mix, so for medication, for business, application again, take it alone. Compounding, right? Continuous compounding, E, or the other compounding. Just compounding, there we go. So continuous compounding is the one we need, E to the RT. But then you have the compound interest, which has that 1 plus R over N. R is constant. So you have that. There is a lot of these different things, guys, that you can do with these. When you have exponential function, you can take the derivative and find change at any instant in time to see how the system evolves. Cool. That's the first half of the lecture, exponential functions, where you are learning and seeing this formula, which is the boss of them all, right? The most general case, any base, any function. Now we switch to its inverses. And the inverses are logarithmic functions. If you are still suffering and struggling with logs, please understand that log is just an operation between two numbers, just like addition is. So please don't discriminate. It's not nice. Accept it instead. I understand that you are well versed with addition and subtraction because you've been dealing with that since before you started going to school. You knew that 1 plus 3 is 4 because 1 and then another 3 is 1, 2, 3, 4. But then you actually sat down and learned and memorized that 3 times 2 is 6, so you don't have to go 3 plus 3 is 6, or 2 plus 2 is 4 plus 2 is 6, right? You learn those shortcuts. If you want to digest the essence of what the log is, you realize that 3 plus 2 is 5, and then there is a backwards operation to retrieve 3 and 2. 5 minus 3 is 2. 5 minus 2 is 3. Now, these are operations that you learn first. Then you move to multiplication to say 2 times 3 is 6. And then the opposite operation that will retrieve these guys, 2 and 3. Then you upgraded yet again. 2 to the 3 is 8. And you said cube root of 8 is 2. But how the hell you get 3 back? Which is where log kicks in. Log base 2 of 8 is 3. So don't discriminate against the only operation that doesn't use symbol, it uses numbers. Probably, if we said maybe 2 heart 8 equals 3, would be better accepted because it's a symbol, it's not letters. But guys, understand, it's just like addition or subtraction. It's computation. And you either sit down to memorize all of its values and figure out how it works, or you don't. What's the square root of 2 off the top of your head? How about square root of 3? How about square root of 4? Right? So you know some. So square root of 1, 1.41. Square root of 1 is 1. Square root of 2 is 1.41. Square root of 3 is 1.7. Right? Square root of 4 is 2. Square root of 5 is 2.23. Right? You can remember these if you want to. But you don't have to. You have calculator for these kind of things. Same thing goes for log. The amount of effort. But don't think it's special. Log is not a function. See, I can make this into a function easy. X plus 2. Boom. Function. I will make this into a function when I say log 2 of x. Right? So, logarithm is operation that will undo exponentiation. So technically, what's log? Equivalent of a subtraction of or division. That's what log is. It undoes other operation that exists and does something. So no discrimination there, and sure, it's the only one that it's odd looking. But I'm not going to apologize for that because I didn't come up with that notation. I would literally use heart for it. 2 heart 8 is 3. That's my notation, all right? The problem is that no one is catching up.
Isn't that why you do the log up there? Just like substitute it in like every lesson in the math book, just like piece of one piece.
Yeah.
Like 5 piece.
Oh, you mean to actually draw the literal log?
Yeah.
Sure. Yes, that's exactly, yeah, here, like this. There's a log for you. You can put a little branch there. Awesome. There you go. 2 log 8 is 3. Perfect.
That's fine.
A little bit annoying to write every time you need it, but it's there. All right. So now that we got that stuff out of the way, we're going to go and see what is the derivative of ln x, which is the, again, specific case. Maybe I should state first that ln x is a lazy notation for log base c of x. So nothing special, it's just 2 characters shorter to write if you write it as ln, which is natural log, because e is the natural base. So ln x is just log base c. As you can see, log base 2, you have to spell it out. So what is the derivative of ln x? And the answer to that is 1 over x. When I saw this, I was really happy and at peace for some time. When I saw this first time as a student. Because it bothered me for weeks when we said that derivative of x to the n is equal to n to the x n minus 1. Right? It bothered me because I didn't know what to do, with 1 over x. Because the integration was issue, right? We'll see why and how. So finally, for me, this story of derivatives and integrals was complete. And I was like, yes, there it is, the missing piece. So now you have this basic one. And no doubt, every calculus student knows this one. But we need this more general. The one that you actually need to know for practical purposes, because this one will be used 99% of the time, is the derivative of ln f of x. The general case when you have any other function but x. And it's very easy. It's dirt cheap. Control C, Control V in denominator, and put its derivative on top. You have the argument of the log, copy, and then the derivative on top. So easy. Insanely easy. And that's the one that I'm going to put on a cloud because, as I said, 99% of the time you will be using this one. And it's not going away in Calc 2, it's not going away in Calc 3, it's not going away in differential equations. If you have to take any of those courses, it will be present in every single one. Again, exponential and logarithmic functions are everywhere around you. So what is the derivative of ln of cosine x? Simple. Write cosine x as is, put its derivative on top, negative sine x, altogether negative tangent x, walk away. You are remembering that you are taking the argument, write it in the denominator, put its derivative on top, and that's it. You're done. That's how awesome this is. The most general case that you can see is going to be log of any base, not just e. ln, when you see ln, you are stuck with a particular base, base e. But if you see log of any base of any function, this is the boss equation. because this one covers all of it. Now it's a log, so we must have this. That can't go away. The only new part here is ln b in denominator. I will box this one, obviously, as important formula. The one that I put on cloud is in here, because remember that ln is base e. If this is e, then this is ln e, and ln e is 1. So it reduces to that formula, sure. So that's the boss equation because it covers log base 2 and log base 10 and log base 13, whatever, of any function. Great. So let's try this equation on, let's find something cute. The derivative of log base, I don't know, 4 of 4 sine x. Just going to write this sine x nicer. What's the answer?
Cosine x.
Yep. What do you do?
Well, first thing I did was I just put ln 4 at the bottom. So that was the easiest for me. Then I put it next to 4 sine x, and then I put the whole rule we did before, which ends up being 4 to the sine x times cosine x times ln 4 on the top. You can cross out the ln 4, you can cross out the 4 to the sine x, and it's left with cosine x over 1.
That's correct. Nice. Or, well, definitely answers cosine x. That's 100%, no doubt there. How'd you pre-calc 1? I know. I'm a terrible person. So early in the morning on Saturday, ask a question like that. The exponent goes in front, log of the same base is 1, so derivative sine cosine, you're done. I know. This is what I'm capable of. Like, be careful. Anytime you see a smiley face on my exam, there's something fishy about that problem. The what?
Beware of the smiley face.
Beware of the smiley face, yes. I need new pen. Textbook example, because the previous one I was evil. What's the derivative of log base 5 of 2x plus 1? That's the textbook example. So here you go. Have fun with that. About that. So what do we have?
2 over 2 times ln 5x plus ln 5.
Times ln 5, right?
Yeah.
That's it. Done. Good. Awesome. Quick. one problem from the homework, and we're done with this section. I hope you're not disappointed.
I used to work for Staples. Every time I want to hear that, I want to kill somebody.
I'm considering getting the button.
My
Good thing I don't have it.
Because I worked cashier, and every person would freaking sit at me anytime they had a good experience. It was so annoying.
Only 2 hours left of calculus one.
What happened?
I said only 2 hours left of calculus.
No.
Hour,
20
hour,
minutes
50
left. 20 minutes left. And then another hour and 20 after that.
Hour. I thought it ended at 1:30. Or then at 1:20 technically.
1:20. Yeah. All right, last question. This is a question 83 from homework. If I hit your homework question, then you just find something else. So find tangent line at x equals pi over 2 for function f of x equals to 2 to the sine x. Beautiful question. Again, find the tangent line is the goal of the class. We happen to have product rule or ln or something. So what's the first thing we do? We find the derivative, right? So dy dx is equal to, put sine x in denominator, ln2, derivative of sine is cosine x, so the whole thing is the cotangent x divided by ln2. Cool? Cool. Slope m is going to be the cotangent of pi over 2 divided by ln2, which is altogether 0, because the cotangent goes through 0 at pi over 2. And we have slope. I have x is equal to pi over 2, and I have m is equal to 0. For y equal mx plus b, I need to find b, but I need y. Well, y is f of pi over 2, which is just 2. Very good. It's 2 to the sine of pi over 2. Sine of pi over 2 is 1, so 2. We plug everything in. So y is 2. M is 0. X is pi over 2 plus b. So b is 2. And what's the equation? Y equals 2. Awesome. So tangent line is y equals 2 because slope m is 0, so that kills the mx part. And you have y equal 2. The other clue that you have, guys, look, the change is 0. Right? Change is 0. No change. So it has to be horizontal line. Yes?
Why did you use that formula instead of e to the x formula? For,
What e to the x?
that's what it was.
For what?
Yeah, for the y equals part, or f of x equals.
To find y, you plug x in the original equation.
No, I just mean like the, that's what I did.
I tried
Why
to use
did-
the
Hold on.
Yeah, the
b
e
to
to
the
the
fx
x
plus
formula.
derivative of fx plus ln p.
I'm completely confused. This is your function, right?
Mm-hmm. And two
Oh
would
my
be-
god, I used the logarithmic.
Yeah. I mean, you got the same thing though, so like.
Wait,
somehow
what?
magic.
No, this is completely wrong. Let me just rip out this page. I can't rip the page out of this, but holy nightmare. Wait. This is, just don't look at this, all right? Look, there's nothing there. Apparently it's the same answer.
Yeah.
I got a different answer. But I'm
Oh,
not
different,
sure
okay.
so much.
I got y equals 2.
So 2 sine x times cosine x, right?
Yeah.
And when you plug in pi over 2, you get 2 to the 1 times cosine 2 times 0, yes, which is, well, actually, no, that goes here. 2 to the 1 times 0 equals 0. Okay. So there was just luck.
Alright. Why is that?
Yeah, it's just time to end this. It's clearly time to end this. Holy nightmare. This is exponential function, and I use the log formula for it. It's supposed to use the...
I thought you were doing some mathematical magic. But you
That
did.
was magic, actually. It worked out, but that was just pure insane luck. I can cross something off the list that I just used like my luck for like next 3 days. This is easy. 3 days of luck right there. Easy.
You can get headshotted in Counter-Strike all the time now.
For 3 days straight, probably, yeah. Yeah, I just want to end this lecture. This is terrible. Okay, so just to wrap real quick. So we have the world of exponential functions and the world of logarithmic functions. They are inverses of each other, so they are linked. You know the derivative of e to the x. You know the derivative of e to the f of x because of the chain rule. But then we get this general formula, which is any base and any exponent, which is exactly what the last problem was, 2 to the sine x. It belongs, well, here, 3 to the sine x. That's technically it. And then we move on. Applications, whatever formula you have that has exponential in it, you will take derivative of it and figure out the instantaneous change, whether it's money or population of frogs or whatever it is. Move to the logarithmic world. We learn this one, which will be around 95% of the time will be this equation, but then there's the most general one, which is this one. Few examples of that. And then we get to the problem. There's a ln2 missing over here. This is terrible. So to find the tangent line. And as I said, every single section in chapter 3 has find the tangent line. The only difference between the way you do it is which type of the derivative you use. The product rule, implicit differentiation, logarithmic differentiation, right? So it's going to be something. All right. And now, the grand finale of taking derivatives. Now, I always say this. I am bound to have one student who's going to find this insanely cool, practice it so much, just to annoy everyone else in the class, and especially when you go to Calc 2. All right? Let me show you something, and then we'll see how well that works. But I'll need your help, because I don't want to cheat. It's called logarithmic differentiation. And I always get excited. I'm actually going to blame the previous problem on me being excited about this part, because this is one of the most exciting parts for me when I teach Calc 1. There are like 4 or 5 spots like this in a course. This is in like maybe even the top one, or in top 3 out of 5. Let's see. Let's come up with something that looks really wonderful for derivatives. For instance, I don't know. How about 3x to the 10 times x squared minus 3x plus 5 to the 6th power divided by cube root of, let's put something interesting here, x squared plus 9. This is going to be fun?
No.
Oh, yeah, it is. So let's see what the derivative of this is. The derivative of this thing, the final answer in the factored form is 3x to the 10 times x squared minus 3x plus 5 to the 6th divided by cube root of x squared plus 9 times all right, so what do we have now? We're going to have 30 over x plus 12x minus 18 divided by x squared minus 3x plus 5 minus 2x over 3 times x squared plus 9. That's the derivative of the top function in a factored form. Like this, as you can see.
Alright, now multiply the two together.
Yeah, multiply it together.
No, you want them in a factored form because now you get to set, set them equal to 0 and solve each piece. This is the preferred form.
So this is what we put on our test.
Yeah. Now to answer your question, which is the central question here. So how, the hell, did I get this? Now, no matter what you give me, I'm going to do it like this just by looking at it. And the trick is that every single one of you can do the same eventually. You practice it enough. And that goes for any derivative out there. And you know what? It erases everything you learned for product rule and quotient rule. And like it zeroes out chapter 3, but you have to be gods of
learn
logs.
this and memorize it and be wonderful at it. We don't need to know anything else.
Yeah.
Alright, let's do it then.
Go for it.
Yeah.
As I said, you have to be gods of logs. So let's see this done on much simpler example, and then we crank it up. And please, if you ever learn this to be such good at this, first time someone tells you, yeah, what do you know? Ask them to take the derivative of something like this mentally. And then just watch them never talk to you again, which is a plus, because whoever tells you, what do you know, especially if they follow that with, I have kids.
Oh my freaking god, I hate those people.
Never, ever, I don't even want to know you exist. Because I haven't heard so far in life that there is a PhD for having kids, in having kids.
Well, as a mother.
Yeah, that's another one. Good. All right.
That makes you more qualified somehow.
Yeah. So let's do this. Cheaper example first, and then we are going to come up with some cool stuff. So say function is equal to just, walk in a park stuff, x cubed plus 1 to the 6th power, divided by also something cute, like square root of x plus 5, okay? So this is a cute example that we will be able to follow easily. So instead of grinding through quotient rule, which contains the product rule with the chain on top and the chain in the denominator, right? We are going to say, I'm going to place ln on both sides because I'm cool. Then the next line is going to look like this. I'm going to use those 3 rules of logs that expand log, and those formulas had no purpose in your math education up till now. So you learned them in pre-calc 1 in section 3.3, I think, and they had no purpose at all until 3.9 in calc 1. I'm going to use log. These formulas are, and I will write them here on the side, ln of xy is ln x plus ln y. Ln of x over y is ln x minus ln y. And ln of x to the p is p ln x. The reason why I had to kind of tread slowly through this was applying the chain rule and using these formulas at the same time. You have enough brain processing power to do those two at the same time, you can actually take derivative of everything mentally. As someone is writing the answer, you start dictating the answer. So here we go. You have a multiplication here, which is multiplication, and you have a division, which is the division in the second row. You have 2 to the 6th and squared and a half as exponents, which is the third row. So all three formulas apply immediately to all of these. So what do I have? I have 2 ln x plus, because it's times, right? 6 ln x plus 3, sorry, x cubed plus 1. And then I have minus 1/2 ln of x plus 5. So this is your pre-calculus 1 section 3.3 from the current textbook we use, where you say expand the log. You expand the log in such a way that there is no exponents on your argument, because they are kicked in front by the third formula. So ln x squared, 2 goes in front. ln parenthesis to the 6th, 6 goes in front. ln parenthesis to 1/2 for square root, 1/2 goes in front. It's times, it's plus, it's division in front of the root, minus. You have to know these formulas to be successful with this method, because this is the first step. What's happening the next is a joke. We take the derivative. On the left-hand side, 1 over y dy dx. I hope you remember that when you're taking the derivative of y in respect to x, you have to follow with a chain. Now, what's happening on the right-hand side? A joke. Derivative of ln x is 1 over x, right? 2 times 1 over x plus 6 times Control C, Control V, and then its derivative on top. Minus 1/2, Control C, Control V, its derivative on top. Do you now see how I quote-unquote cheated? The formula clearly says over here, now this y has to go to the other side. So the derivative is y times 2 over x plus 18x squared over x cubed plus 1 minus 1 over 2 times x plus 5.
It's kind of dirty since it's already fully factored.
And you see that you get to copy the entire function that you started with. So now examine my answer. How did I do this? And no matter what you give me, I'm just going to do it like that. Look. We copy the constant, the derivative, the exponent 10 goes in front of the ln, so 3 times 10 is 30. 30. And derivative of ln of x is just 1 over x, so 30 over x on the first one. On the second one, 6 goes in front, so I have 6 ln of this. Well, copy this in denominator, which I did. Derivative of this times the exponent, that's 2x minus 3, 12x minus 18. Jump to the next one, minus, because it's on the bottom. If I have 2 or 3 of these, doesn't matter how many you chain, all that are on top will get pluses, all that are on the bottom will get minuses. The procedure of how we get these is the same. So that's 1/3. Here's my 1/3. And then I have x squared plus 9, copy and paste. Its derivative is 2x on top. Because it was 1/3, I don't have to worry about multiplying by anything. Done. Times. This is your y from the formula, which is the original problem. Every derivative you can possibly think of is done this way instantly. Takes care of the product rules, chain rules, quotient rules, anything you can come up with. We can go back and do every problem this way just by looking at it. Now, it takes time to figure out what goes where, and obviously, if you're writing everything out, it looks abysmal and long and terrible. But if you have enough computing power to see the basic operations that are happening, it's cheap. So what do we have say for product rule. Y equals x squared sine cubed x. This is x squared times x cubed, sine cubed, which means product rule and then chain rule, right? Can I do this logarithmic differentiation quick? The answer is hell yes. Install ln on both sides. We have ln y is equal to 2 ln x plus 3 ln sine x. The next is derivative, and we are done. So what do I have? 1 over y dy dx is equal to 2 over x plus 3 goes on top, sine x as is on the bottom, derivative of cosine goes on top, and the next line is the answer. Multiply y on both sides. Y is x squared sine cubed x times 2 over x plus 3 cotangent x. Walk away. Product rule is not going to give you factored form. Do you have to know this? Nope. By far the coolest thing in the entire chapter. By far the coolest thing, in my opinion.
When it's 3 ln parentheses sine x, which changes to 3 cosine x over sine x.
Mm-hmm.
How are you
The derivative is always f prime of x over f of x. So, and this is your f, right? So copy it as is, the derivative of it on top, copy the 3. You don't have, well, it's hard right now because you don't have the grasp on. One negative about these Sundays classes is that I don't have to see you twice a week. I time that so that you guys see the log first and then I cut it. But I have to teach one more section today if we are to stay on schedule. Now, luckily, this is just me telling you the next section. Memorize this and walk away. But the thing is that, you know, if this was kind of a 2-day deal, I would actually teach the logs and I would stop the lesson before I introduce this. You would go home. Let's say it's Tuesday, Thursday. You will learn Tuesday. So from Tuesday to Thursday, you would learn this, which is what we're using 100% for these. You would learn that one. And then when you see the derivative of ln of sine x, you just say, okay, that's the denominator. The numerator is its derivative, and then the final answer simplified cosine over sine is cotangent. But you don't know this yet because we just learned it. So the whole logarithmic differentiation thingy is not as valuable because you're confused where is the stuff coming from. But once you get the other thing clear, and only when that's clear, combined with the log, with the ln log formulas for expansion, any derivative becomes child play. But you have to be very good at decomposing, right? Expanding the logs. Now, this is useful for your chapter 4 because remember, the derivative is going to be the first step of the rest of the problem, just like for your tangent line, right? So now you would have to set this equal to 0, then solve for x, then do the rest of the problem, right? So, which in this case, guys, is not that bad. X is equal to 0, sine is equal to 0, so the first one is producing zeros, the second one is producing pi's, and then whatever the hell we get from the third one, which actually can be solved without graphing. That's the one where you have to actually graph to solve. Ooh, that's really cool. I was just looking at how to solve this real quick. You will have to do this in chapter 4. And I just realized that if you move the term to the other side, which you have to do every time, unless you can factor, if you flip one side, you flip the other side, so you get x over 2 is equal to negative 3 tangent x. So technically, you get that the tangent x is equal to negative x over 6, which is easy to graph. You can't solve this by hand. You actually have to graph and then look for intersections and so on. And then negative x over 6 would look something like this. So they intersect at 0, they intersect here, and here, and here, and so on. And all of these have x comma y, right? So you pick x's. Awesome. Not the part of chapter 3, so I'm going to get rid of this. I was just happy to see that it will work like that. Let's see one example from homework, for this stuff. And then take another short break. Ooh, they have cute problems. Let's try this one. Sine x raised to the tangent x. Like, why? Because we can. That's why. So we know the procedure, right? ln of y is equal to tangent x ln sine x. When we put ln in front of f of x, which is y, and ln here, the power formula will put tangent in front of ln. So now when you differentiate, you have a product rule on the right. Right? You do the product rule. On the left, you just have the vanilla 1 over y dy dx. All right, so try if you are stuck. There is the step. Do the product rule. No pressure. You have 18 seconds.
I went to Alexa last week.
And that's the end of the section now. So let's just go through this problem together. We apply ln to both sides, and we use the power rule to peel off the exponent, put it as a product there. And I have the product rule on the right. Left-hand side is the chain rule. Derivative of ln y is 1 over y dy dx. Copy the first derivative of the second, plus copy the second derivative of the first. Cosine over sine is cotangent. This is sine over cosine, so you cancel sine to get cosine, you get 1. Do we all get that? Yes, sine over cosine, it cancels completely. It's 1. And then you have secant first, we put ln second. So that's what we do.
Why do you not break down ln sine x to be
This one?
so sine over sine?
Well, that's the product rule. You copy this from now. So you copy first, you take derivative of the second, then you copy second, and you take derivative of the first, for product rule.
So when does it equal 1 over x when it's just ln?
Just ln, yes. So The question is, when is the derivative only 1 over x? That's just when you have ln x, the top formula. But see, if this is x, you would put x over here, and the derivative of x is 1, right? So that's the boss for ln. All right, restart the stream for the next